this question, we can see that we have to find the poles and zeros of the following waveform and plot the results on the pole zero diagram. But first we need to know what is the poles and zeros, and we have to first know about that. And let's see, we can write a general equation for the transform Vm minus 1 Sm minus 1 and so on B1s plus B naught divided by ANSN plus AN minus 1 S to the raised power n minus 1 plus so on plus A1S plus A naught. In this waveform, this is actually a transfer function in the transformed form of any polynomial or any waveform, and this can also be written in another way. This is a kind of generalized form, and this can also be written in the factored form. In the factored form, we can represent the same something like Bm over A n into S minus Z1, S minus Z2 and S minus Zm divided by S minus P1, S minus P2 and so on S minus P3. So any form, any waveform for any system or circuit can be represented in this form, and this form is the most generalized form. And this form can further be written in the factored form. Factored means that this has been factorized and given the factors this way, and this is also factorized and given the factors this way, and these are the highest coefficients, which are also known as, this one is also known as scale factor and can be represented with K or anything. And in this one, we have deliberately shown these as Z's. Z means these are actually the zeros, and P means these are actually the poles. So the roots which are present in the numerator of any transfer function, those are called the zeros of the function, because if for all the values of Z1, Z2 and so on till Zm, where m can be for m is equal to 1, 2 and so on till m. So if you place the value for these values, this whole function will become actually 0. For any value of the 0, the whole function can become 0. So these zeros can make the system as zeros. Similarly, on the other hand, in the denominator, you can see these are the poles, and these poles for all n values 1, 2, 3 and so on till n, these can make also the system to vanish. So these are two extremes which can be quoted in this way. So these are called the zeros and the poles, and these zeros and poles can be represented in the S-plane. And these zeros and poles actually represent the behavior of the system, and poles can tell whether the system is stable or unstable. So this was something about the poles and zeros, a little theory about that. Now we will actually move towards solving the circuit. Not the circuit, actually this is the already given in the waveform. Okay, so here you see, first you have to take taking Laplace transform this has taking Laplace transform f of s, this time is converted to, is transformed to the s domain or the frequency domain. Now we have to write the Laplace transform of these two multiplied with unity, because the Laplace transform does not exist before time 0, so this we always multiply it with the unit function, because unit function is starts from 0 and then moves till the positive infinite side. So from the Laplace transform table we can directly simply apply these formulas. So first for this one, e to the raised power minus 10t and cos 2 of t, we can use this transform, which is actually s plus alpha, here is 10 and divided by s plus 10 square plus beta is actually 200 square plus this factor will stay here the same way, and now beta will is 200 divided by s plus 10 whole square plus beta is 200 in this case as well, we can see. So now we only have to simplify it first. S plus 10 s plus 10 divided by s square plus 20 s plus 100 plus 2 to the 4, and this is 40,000 actually, plus this is 1 divided by s square plus 20s plus 100 plus 40,000. This is actually 10. Okay, here we can take the LCM. So s square plus, actually in the denominator was the same, we could have taken the LCM already, but anyway, so this is s plus 10 and 10 20 because the denominator is already the same. So this is s square plus 20s plus 40,100 is. So we have found the transfer function in the S domain, and you can recall the generalized form. And now the denominator we have to factorize it. For the factorization of the denominator, we can apply the quadratic formula. So S is equal to minus B, which is 20 plus minus B square minus 4 A and C, 40,100, and 2A is 2. So minus 20 plus minus, this is 400 minus, this is 404041 the 4, 4044 the 16, divided by 2. You have minus 20 plus minus 400 is subtracted out, so 16, 160,000 for us. Now we can minus 20 plus minus J, 400 divided by 2, so we got so you can write it S plus 20 divided by S plus 10 plus J 200 into S plus 10 minus J 200. So we can simply see here now, this is going to give us the zeros and this is going to give us the poles. So first, 0 lies at zeros, it lies at minus 20, and the poles are actually, we have minus 10 plus J 200. The second one is minus 10 minus J 200. Since we have two poles, the poles and zeros must all be the same. So one zero lies at minus 20 and the second zero will be at S is equal to infinite. So the one which cannot be realized, that is automatically considered to be lying at the infinite. Now we only have to plot these poles and zeros in the pole zero diagram. This is our S domain plot. This is J omega. We can simply see minus 20 is our 0. So let's say this is minus 20, and the zeros are generally represented with the help of zeros. So this is our first zero. The second zero is lying at infinity, so that cannot be drawn, that cannot be mentioned. Next, the poles are 10. So this is actually minus 10. This point is minus 10. And on the J axis, we have it about 200. So this is, let's say, minus 200 J, and this is plus 200 J. So minus 10, this is our first pole, and the second one is, this one is our second, and this point is actually minus 10 plus 200 J 200, and this point is actually our minus 10 minus J 200, and the poles are generally represented with the cross in the pole zero diagram. So this is our pole zero diagram, and according to this pole zero diagram, since all the poles lies on the left half plane of the S domain plane, so this system or this pole zero diagram is representing a waveform of a system which is actually a stable system. So that's all for this topic. We will solve another question of this topic soon after this. Okay, we just finished the first question of plotting the pole zeros, first finding the pole zeros and then plotting them. And this is just another example, and we are going to solve it. First we have to take the transform of this f of s is equal to e to the raised power minus 2 of t. The Laplace transform of e to the raised power minus 2 of t, that can be also seen from the Laplace transform table, and according to that this is s plus 2, minus 2 is going here, and cos of 2t we just have used it also. This will be s over s square plus 2 to the 4, and this will be 2 divided by s square plus 2 to the 4. So this is our, and now we can just simplify it again to get a transform function in a more better form. So s plus 2 into s square plus 4 is the least common multiples, and we have found this s square plus 4 plus s into s plus 2 minus 2 into s plus 2, and simplifying this s square plus 4 plus s square plus 2s minus 2s minus 2 to the 4 and divided by s plus 2 into s square plus 4, and from here we have found 2s square. These are cancelled out, plus 4 and minus 4 is also cancelled out, so 2s square divided by s plus 2 into s square plus 4, and clearly you can also write it 2s square s plus 2 into s plus j2 into s minus j2, s square minus plus j square will give plus and 2 to the 4. And from here we can simply see that our zeros are zeros and poles. Poles are, first we can write the poles minus 2 and then minus plus minus j2. So we have 3 poles in total. And zeros, 2s square. So we have 2 zeros, first 0 at 0, the second 0 at 0. Actually you can also write s is equal to and s is equal to these. And the third pole is actually lying at infinity. So we have these zeros and poles figured out. Now we just have to plot them on this pole 0 diagram. And the first 0, you see, this is first 0, this is second 0, just to show we can make small zeros and big zeros, and the third cannot be plotted. Now we have to plot the poles. The first pole is at minus 2, the second and the third are conjugate poles of each other. So this is like, let's say there is the j2 point, and similarly here is the minus j2. So there is no real part in it. So these are actually our 1, 2 and 3 poles and 2 zeros. The third 0 cannot be plotted, and this is our pole 0 diagram. Again, in this, for this waveform, for this system for which this waveform is obtained, for that one it shows the system is again marginally stable and marginally stable, because this is totally showing the stability. But if the poles are lying on the imaginary axis, then it means that the system is marginally stable. So this is all for the pole 0 diagram, and with this one we have completed actually the topic of finding poles and zeros if the waveform is given, and how to plot those poles and zeros in the pole 0 diagram or in the S domain. That we also have concluded and plotted and concluded this way. And good luck to you all, guys. If you have any particular question regarding any topic, and if you have or you may have some difficulty in solving any question, you can simply post that question in the comments, and I can try to solve it for you guys. Welcome again to see my all videos, and I wish you good luck that you can understand the topic. And for any problem, you can simply comment and request for the solution. Goodbye till bye.